Hello, a very good morning to all of you. So today we will start a new topic on regression. Not actually new, but we have covered what regression is. Just to give a small recap, what do we mean by regression problems? So far we have talked about two kinds of prediction problems, right? We've talked about two kinds of supervised machine learning problems. They are largely prediction problems. One is classification. Another we have talked about is regression. Classification is all about predicting a discrete variable, while regression is all about predicting a continuous variable. We have seen various examples also. Uh, we've talked about predicting whether an email is a spam email or not. That's a classification problem. Handwritten digit recognition problem. Again, that's a classification problem because my classes are fixed from 0 to 9. Right? Spam or not spam. Again, it's a binary classification. When it comes to regression, I'm going to predict a continuous variable, just like predicting a house price, predicting a stock price, but forecasting sales value. These are all regression problems. Now we will learn in today's session, we are going to learn the mathematics behind a regression problem. So what we typically want is we are actually in machine learning, what happens is we are given a data set. Let's say in the form of a very tabular format, right? We are given a data set like this. So we have some n samples, right, from 1 to n, and there are certain dimensions, right? Uh, this is x1, this is x2, this is x3, and so on, right? And last is the label data, right? So let's say if I am talking about predicting house prices, so I need a historical data of the houses which are sold in the past. So basis that, I will create a model. So this is what we call x1, x2, x3 as input features, and y is my output, the target, the house price value actually. So this data is already available with me. So now what could be x1, x2, x3? X1 could be the area of the house, the size basically, or x2 could be the number of bedrooms, whether it's a furnished or unfurnished house, x3 could, so there could be n such number of uh, features, input features that I have in the data set. I'll have one output feature, that is the house price. It could be of 25 lakhs, 35 lakhs, 50 lakhs, 1 crore, and so on. Now, in a regression problem, given the set of input features, right, we want to predict the output feature, that is the house price. So, using the historical data, the model will learn an equation. That equation will depend on how the, let's say, the size or the area of the house is affecting the price, how the number of bedrooms are affecting the size, how the furnishing is impacting the price, right? So each of these features will have some weights associated with it, right? We call them as like theta 1, theta 2, theta 3, and so on, right? So the objective in case of regression problem is to learn these weights theta 0, theta 1, theta 2, theta 3 by training a model. And once I have learned the weights, that can be used to uh, sort of predict um, the house prices of the future houses which will be sold, right? That's the idea behind regression problems. So when you look at the examples, it's not only house price. I want to predict, let's say, the height, age, right? No, not height, age, sorry. I want to predict the weight from gender, height, age. I want to predict the house price from locality, area, income. I want to predict Google stock price today from the prices yesterday, right? So these are all examples of regression problems. Now, regression equation could be as simple as, if let's say I'm only considering area of house as input, only there is one feature, price is the output. So only one input feature is there. So the equation could be very simple, theta 0 plus theta 1x. This is simple linear regression equation. Right? While if there are more features, the equation will turn out to be theta 0 plus theta 1x1 plus theta 2x2 plus theta 3x3 and so on. Right? Now, maybe the house price depends on number of input features. Right? So that is generally the case. To understand how the regression works, we may take simply one input attribute and then say, okay, this is how the prediction does, or this is how the regression works. Now, this one important term known as correlation, which we have covered in the last session also, which is defined by this formula, covariance of x and y divided by standard deviation of x and standard deviation of y. So x and y are the two variables, and how they are related, that's what correlation determines, right? So if you look at this graph, the correlation could be negative, as you see in the first graph. Second is also negative, third is also negative, meaning that if you increase one variable, other one is decreasing. While it could be positive also, if you increase one, the other one is also increasing. Second thing about correlation is the magnitude. If it is close to -1, it's a very strong negative correlation. If it is close to +1, it's a very strong positive correlation, right? If the correlation value is 0, then the two variables are independent. They don't impact each other. This is the case, right? So now, how to solve the regression problems? Objective, as I told you, I want to find out the weights, how much every input feature is contributing towards predicting the house price, right? That is what I want to learn. And there are two different ways to learn those weights. One is using a direct closed form equation. This is quite mathematical in nature, that directly computes the model parameter that best fit the model to the training set. Second is, it uses an iterative optimization approach known as gradient descent that gradually tweaks the model parameters to minimize the cost function over the training set, right? And eventually converging to the same set of parameters as the first method, right? So typically this is all mathematics, right? When it comes to gradient descent approach, this is more of an iterative approach. Uh, Here only you will solve the equations and get the best parameters, while here you will start with some parameters, some weights, and gradually move towards uh, optimizing those weights, right? So we are going to see both the operations today. So when you look at least square approach, right, we call it as a least square approach. What do we mean by least square approach now? Let me explain it here. And let us say this is a two-dimensional plot and I have some points. And I want to, let's say, fit a line. I want to fit a line. And now, what do we mean by least square approaches? Now, there could be multiple lines that I can fit, and that's what the linear regression is, right? Fitting out a line, straight line. But some of the points you see, they fall on the line, while some of the points lie above the line, and some of the points they lie below the line also. Now, the distance of the point to the line is called as the residual error. So we find the distance of every point to this line. If the point lies on the line, this distance would be 0. If it lies above the line, this distance would be positive. If it lies below the line, this distance would be negative. What we typically do is, what is the line that I want to choose? Because I can draw infinite lines from these points, but I want to choose a line that minimizes the overall residual error with respect to all the points. So the points which lie above the line with a positive residual error, and there are points with the negative residual error. Right. So if I simply add them up to find out the total residual error, it may be possible that the magnitude of positive is equal to the magnitude of negative residual error, and they cancel each other and the residual error comes out to be 0. However, the residual error is actually not 0. 0 means the line is passing through each and every point. That is what the residual error 0 means. But we know that there are some points that lie above the line. There are some points that lie below the line. So what we do typically is the distance of the point to the line, right? We take it, and the points which lie above the line, they are already positive. The points which lie below the line, they are negative. So we scare that error. So let's say distance of point 1 with respect to the line is E1. So we'll take the distance as E1 square, then plus E2 square, plus E3 square, plus E4 square, right, up to En square. Now the negative distance will also, when you scale it, right, it will become positive. Now it will give you the actual value. What is the overall residual error? And when you sum it across and then divide it, that is where we want this value to be minimized, divided by the total number of points, because you want to average it out also, right? So if there are n points, with respect to each point, there is an error of E1. Error means residual error, that because it is not falling on the line, so that is typically termed as an error. So you will sum it across and then you will divide it by n, and you want to minimize it. The line which will minimize this, right, which will have the minimum residual error, that will be termed as a best line, and that is where those theta 0, theta 1 I will pick up and say these are the best theta 0, theta 1 for predicting the house prices based on the area. Now we have least square approach, as I mentioned, right? So I am scaring it, and whichever will give me the least value of that residual error, that is what I'm going to pick. Now, if you see the lines drawn here, these are the points, right? What might happen if you're trying to put up a straight line, that becomes a linear regression. When you feel that, okay, straight line may not be a right fit for this kind of data, so you actually try to come up with a polynomial regression. When you have a polynomial regression with degree 2, that is known as quadratic regression. So it will be a curved thing, right? It will not be a straight line, it will be a curve actually. So the green one that you're seeing is a curve, and that's of degree 2. That's why the name is quadratic regression. Otherwise, it's a linear regression. The red line is a straight line, which is a linear regression. Overall objective is that the error either from the curve or from the straight line should be minimized, right? That's the idea behind linear regression or overall regression, I would say, right? So you look at this, as I mentioned, you want to come up with a straight line. Now there are points which are lying above, there are points which are lying below. So what do you want to learn is the equation of the line is theta 0 plus theta 1 x, right? So here it is written as theta 0 is written as b. So that's also okay, right? We want some parameter, that's all it is. So this is what my model which has learned theta 0, and it could be like this, like y is equal to 5 plus 4x, let's say, right? So this is one model which has been learned. Now this is what the model has learned these parameters. Theta 0 is 5 and theta 1 is 4. Let us assume that way, right? So what you will do is, now you want to find out the mean square error, MSE. So how will you do that? Y cap. What is Y cap? Y cap is nothing but what the model will predict. You will give this X feature, and now model parameters are known 5 plus 4x. I am just assuming if these are the model parameters that have come up. So you will just put the value of, let's say the value of x is 10. So 10 into 4 is 40, 40 plus 5 is 45. So y hat will be 45, right? Minus yi, the actual output which is available with me, right? So what you will do, you will take the predicted output, prediction by the model, the actual output, scare it, right? And then this has to be done for all the points if there are m points, right? So you will do the summation from 1 is equal to 1, I is equal to 1 to m, and then divide by m. So this is what the mean square error that will you will come across, right? The idea is to minimize this mean square error. So how do you put that mean square error? This diagram again showing some points lie above the line and some points lie below the line, right? And if there are more dimensions, like you see this is a 3D. In 3D, the straight line will become a plane. So some points will lie above the plane, some points lying below the plane. So overall error we have to take is by finding out the straight line perpendicular distance, scare it, because there is a positive residual error, there is a negative residual. We don't want it to be cancelled out. Scare it, then add it, and then take the average. So j theta is equivalent to, what is j theta now? What is this cost function? How this scary term came in, right? Now that's the question. So this is one way to represent a cost function. What is a cost function now? Cost is, if you look at this equation carefully, this is measuring the error only, right? This is measuring errors. This is my prediction. This is my actual output. H theta is basically my theta parameters. Xi is my observation, right? So it is like 5 plus 4x kind of a thing, right? Now x we have to put. So once we put the x, let's say if it is 5, 5 into 4, 20, right? Plus 5, 25 minus the actual output. So it is actually the same thing, the residual error we are calculating. The objective is to minimize it, right? So when you sum it across, so this is the cost. Cost means this is the error that we are getting, right? Now the term cost function is used. We want to minimize it because error has to be minimized so that so that line is close to the every point as far as possible, right? That is what the objective. We want to minimize it. So how do we minimize it? We can minimize it by saying, okay, we want to solve the now minimization problem. So minimizing j theta. So now we have converted our regression problem into a minimization problem because the least square method or least square linear regression has turned into a function, right? And I want to find out the minimum value of that function now, right? This has turned out a now mathematical problem which we can solve using derivatives and all. And that's what we are going to do, right? So as I mentioned, if I want to predict the house price, if I take a very simple case that I want to predict the house price only basis area. So my equation will be like this: theta 0 is equal to theta 1 plus x, theta 0 plus theta 1 x, right? But what if there are multiple input features? It could be proximity to the market, it could be proximity to the schools, it could be whether there's a granite marble flooring or not, how many bedrooms are there. So there could be n number of input parameters basis which I want to predict the house price. Now, with each input parameter, there is a weight associated that is known as theta. That is how much it is contributing towards impacting the price of the house, right? So the equation when there are multiple input features, it is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta d xt. If there are d input features, right? So then there will be d plus 1 weights that we want to learn. If you look at depending on the area, we want to predict the house price. The equation I'm saying is theta 0 plus theta 1x. So there are two parameters, right? One, how much x is impacting the area of the price is impacting the area of the house is impacting the price. Second is the intercept, right? That is there always in a straight line. So there will be an intercept also in a multilinear regression, right? If I'm saying the term linear, it means again I'm trying to fit a straight line, but with multiple parameters this time. That is x1, x2 up to xt, and then my y is a kind of theta j xj, right? So now you look at it, once I have found theta, right? So I will apply this theta matrix to a particular observation and it will give me the predicted value. It will give me the predicted value. For example, let us say I have come across, I have three factors like theta 0, that is, let's say 1, theta 2, 3, sorry, theta 0 is 1, theta 1 is 3, and theta 2 is 4. My equation is, let's say, theta 0 plus theta 1 x1 plus theta 2 x2, right, with 3 input features. So this will turn out to be 1 plus 3 x1 plus 4 x2. 1 plus 3 x1 plus 4 x2. So now what xi will give me? Xi is a particular record within the data set. So it will have the value of x1 as well as the value of x2. So I will give that value of x1. Let's say the value of x1 is 2 and value of x2 is 3. So 1 plus 3 into 2 plus 4 into 3. So 1 plus 6 plus 12, right? So total it is 90. Now I know I have the actual output also available. So I'll see the model which has learned the parameters, what is its predictive value and what is the actual value. I take the difference. If it is exactly predicting same as what the actual value, this difference will be 0. Otherwise, there will be some difference and I'm going to scare it, right? And this is what I'm representing in the form of a cost function. Now the problem has converted towards minimizing this cost function. Now with respect to this, right, how do we minimize this? That's one aspect of it, right? Minimizing it, we will do it in a different method known as gradient descent. I talked about two methods. One is closed form equation, another is gradient descent. Using closed form, we directly calculate the parameters, while using gradient descent, we start with some parameters and then it's an iterative process. The model learns the best parameters over a period of time, right? So that part we will see in the second half of this session. But in the first half, we will look at the least square method, right? Now, all of you have covered relational algebra, right? You know the matrix multiplications and all. So here I am going to use some form of matrix multiplications to represent these equations in a different way so that we can solve the best value of, we can come up with the best value of theta, right? And that's what you must have learned in the lab session also, NumPy and using NumPy, because in NumPy you have all those 1D arrays, 2D arrays, which are nothing but largely the matrices, and you are performing some operations on these matrices. And that library is highly optimized for these matrix operations and so on, right? Now, what we will do, we have hx as theta j xj, right? J is equal to 0 to d. So it's the same thing. If you put j is equal to 1, theta 1 x1, theta 2 x2, theta 3 x3, and so on, right? And normally, if you look at it, we put one extra feature because there is a weight theta 0. If I simply say x0, right, it will become theta 0 x0, the first thing. Now this portion has always to be 1. So whatever the input features are there, x1, x2, x3, x4 up to xt, I will always add a 1 to it, right, to a set of input features, so that my theta 0 gets retained. So this value will be 1, so this will become as theta 0 only, right? Theta 0. Now if you put 1, it will become theta 1 x1 plus theta 2 x2 and so on, right? So theta also we are representing in the form of a vector. Now you look at this side, right? This is 1 cross d cross 1. There are d rows. If I have to write it, this is d cross 1 x transpose, right? X transpose. So this is normally, if I look at this, this could be like this: the value of the first feature, second feature, third feature up to dth feature. Now, if I have taken a transpose of it, this becomes a matrix. This is a matrix, so I can take a transpose of this. So row has changed into kind of a column, so this has become this, right? This has become this. Now, hx is theta j xj, theta j xj. Now, if I take theta transpose, so this will become like this: theta 0 plus theta 1 plus theta 2 up to theta d. If I take the not plus, sorry, theta 0, theta 1, theta 2 up to theta d. Right? Now, if I take x, x will be 1, x1, x2, x3 up to xd. So this is nothing but theta 0 plus theta 1 x1 plus theta 2 x2. So the same thing right here, this particular thing, we have written it in the form of this. Few students have joined. I'm not sure whether you're able to follow. You can let me know if you're able to follow or not. But it is disheartening to see none of you joined initially. May I know if you're able to follow or not? Will somebody please tell me? Okay, no response. It's fine. I will simply unmute you. If you want to speak, even you can speak. Otherwise, I'll do my job. Now, let's expand this further, right? We already know this is my theta vector, right? Which I can write like this. X is a set of, now this is a complete data set that I'm talking about. This is the first row of the data set, right? This is the second row of the data set. Sorry, dth row. and this is the nth row, right? So basically, if I look at the theta, it is D plus 1 cross 1 matrix. And if I look at the data set, it is N cross D plus 1 matrix, right? So H theta X, right, which I want to apply on a particular observation is X, which is N cross D plus 1 multiplied with theta. So all of these will be multiplied with this. So it is theta 0 plus theta 1 x1, theta 2 x2, theta d xt. And then for the second iteration also, it is theta 0 plus theta 1 x1. So now whatever we were doing it for a single record here, now we are doing it for with the complete data set. Now X represents a complete set of input features of the data set. Theta is the model parameters. And if I multiply this, this will give me all the predictions, right? And if it is giving me all the predictions, now I know my cost function is this. This we have seen. Now H theta X, I know it is this X theta, right? So this is theta transpose. Theta transpose will give me a vector like this, right? Theta transpose xi, I think this we have seen here. Just a minute. Yeah. This is theta transpose xi, right? Same thing I am going to apply here as theta xi is theta transpose xi minus yi. Now if I solve it, this is complete mathematics. Now this theta transpose xi is my x theta, right? I know that this is my x theta. Because I am going to come up with that equation, and finally this h theta x is going to be x theta, right? Because this will become this is now for all the observation. I'm applying this theta value to all the observation. So this is exactly this thing. If you see, I'm applying all these weights to first row, then second row, then nth row. Same thing is happening here, right? I'm applying to each observation, the first row, the second row, the third row, and so on. And then at the same time, I'm subtracting that, right, to find out that particular error. Now further, if I solve it, this particular thing is x theta minus y transpose multiplied with x theta minus y, right? Now what is y? Y is another vector of outputs. So what is the output corresponding to first record? What is the output corresponding to second record? What is the output corresponding to third record, and so on. And this is the cost function. When I write it like this way, x theta minus y, right? And then x theta minus y, because this was a square term, right? So when I do this portion, so this becomes x theta minus y and x theta minus y, come this particular thing, right? And now we've got this j theta in terms of vectors. We've got j theta in terms of vectors. Now, even if I have to show you how this is come is, I told you this is error term with respect to each vector, right? So when I say theta transpose xi, this is my prediction with respect to that, and this is my actual output. So this is actually with respect to the first observation, the error 1 scale, right? Error 1 scale, and I varies from 1 to n, then error 2 scale. So with respect to all the points, this is calculating basically error. So this will become, if I have to write it right, maybe this will become like this. So if you look at this x theta minus y, right? This is theta transpose xi minus yi square. So basically, this is all is this particular portion is the E1 part, right? This particular portion is E1 part, and E1, E2, Et in this form it will come. And when I use this x theta minus y, now there is no transpose over here, right? So it means this will come in this form. So ultimately this is equivalent to this because you multiply this with this with this. This is a simple multiplication of matrices now. So this particular thing has been broken into these two mathematically, right? So this is now the cost function, right? Now we've got this cost function as this. Now if I further solve it, right, I multiply this x transpose theta transpose x transpose x theta, right? This multiplication we have done. Then y transpose x theta we have done, right? Then this particular y will also get multiplied. This is theta transpose x transpose y transpose y, right? These two terms yt x theta minus theta t xt yt, right? This will ultimately become 1 cross 1 matrices, and I will simply write it as this particular form. These are two things, right? I mean, two ways of representing the same thing. Because if you see here, it is without transpose, right? Being getting multiplied. Here it is with transpose, but y is same. Here y is getting transposed, right? So it is simply written as this way. Y transpose y is same. Now we want to minimize it, right? When you do want to minimize it, you do a derivative with respect to theta. So there's no theta involved here. This term will get 0, right? So when you solve it by using the derivatives, you got this particular thing as 0. Our objective is finding out theta. So theta ultimately becomes x transpose y, x transpose x inverse, x transpose y. So this is the final thing that we got using closed form solution. Now, if you don't know derivatives, you have to revise that from your mathematics class, right? How to find out the derivative, specifically the partial derivatives, right? Because this is with respect to theta. So this is x transpose x theta, right? Minus x transpose y. Because with respect to theta, we are doing it. So that term will actually go off, right? So this has to be put to 0 because we want to minimize this, right? And this function has to be minimized, right? So finally, at what value of theta this will be minimized? This is what we got, right? Now, when we are given a data set, we are already given x and y. Both are given to us because that is a structured data set. Now I want to learn parameters. I can simply apply this equation and find out the parameters. This is nothing now, matrix multiplication only. I hope it is making sense so far. If you can respond, that will be helpful. No response. Okay, fine. That's up to you. Now, if you're asked to find out the solution, right? I think you should be able to figure it out the solution using this equation. Now, let me say that, okay, let me take a simple example rather than this particular thing, right? I have some x feature and some y feature, right? These values are 1, 2, 3. These values are 4, 5, and 6. Or let me further simplify this. Let me take this as 2, 2, 5, 6. Not 5 even, I would say, let me just simply do 2, 4, 6, right? X is this, Y is this. Model parameters you already know, right? So this is my input, this is my output. I am taking only one feature. So let us say the Y is theta 0 plus theta 1x. These are the two model parameters that I want to learn. So what my X will become? This is my input, right? First row I will have to add to find out theta 0. Second is, that is what I will do, right? Output vector is 2, 4, 6. So Y is also given to me as 2, 4, 6. What I need now? I need X transpose. First thing I need is X transpose. If I want to do X transpose, I can do it like this way, right? Then what I need is X transpose X. So I can multiply X transpose with X, right? And then whatever the value comes in, this will come out to be approximately like this, 3, 6, 6, 14. You can multiply these two and you will find out. And second major portion is finding out X transpose X inverse, right? Because you need that. If you look at the equation, you need that. So if you find out that inverse part, so you will end up in finding out as 1 by 6, because you will find out the determinant. X transpose X is 3, 6, 6, 42. 14 into 3, 42 minus 36 is 6. So 1 by determinant, right? This is what you will end up in, right? And finally, you need X transpose Y, and that you will come across as 12 and 28, right? So you have got X transpose X inverse, X transpose Y, right? So what is this? The multiplication of these two is left now. You can multiply these two. So you will learn the model parameters as theta 0 will come out to 0 and theta 1 will come out as 2. Basically, you will get this matrix 0, 2. Because this is 2 cross 2, this is 2 cross 1. So ultimately, you are going to get 2 cross 1. So your model is only y is equal to 2x, and that's what this is, right? So simply y is double the value of x. So we've solved it using the equations also, right? So look at this, we can solve it also using the equations which we have learned. So instead of this 1, 2, 3, right, we have to write these four values. In within y, we have to write these four values. I didn't take it because otherwise the calculations will become too heavy. So even if you are asked to solve a solve using a closed form solution, so this is the equation that you should go with, right? So this was a bit about closed form, right? So when you do this closed form, right, So there are advantages, right? This is a mathematical equation, no iteration required. This will be very, very fast for small data sets like 3 records, 5 records, 10 records, which we have taken. What if there are too many features within the data set? There are one feature that we have taken, right? What if there are 500 features? See the matrix size, right? Then this will become computational heavy. And further, you have to compute the inverse of a matrix, right? Inverse of a matrix is again not very easy to compute. So this will become quite a memory intensive thing, right? So for a very small data sets, yes, this is a good approach, but for very large data set, this is not a good approach. And that's where the other approach, gradient descent, is used in largely in machine learning algorithms, because you're dealing with huge data sets. Right? Now, it is a similar same thing, right? But represented in a different way. So there's a cost function, there is a scared error cost function, right? You are predicting it, you are subtracting it from the actual value, right? And you are finding out those weights basically. So the cost function will indicate how good or the bad the line is. So if these prediction errors are huge, cost is high, right? Then of course the line is not that good. But when the prediction errors are small, the cost is low, right? So the cost is minimum, right? So then you can assume that, okay, yes, my line is good. Right? When you look at this again, the same thing, right? Now for insight on J, let's assume that X belongs to R. So theta is equal to theta 0 and theta 1. Simplistic parameters that we have taken, right? So for a fixed theta 1, this is a function of X only, right? So if you fix one of the parameters, this will become a function of X only. Theta 1 is always 1, right? So the line becomes a function of X because theta 1 is not changing. Theta 1 is 1. So whatever is the input size, right? Simply we are adding that. Now only the intercept will decide where my value should go. So if you look at theta 0 as 0, right? Then this function only becomes, you can say, uh, depends only on theta 1. So rather than writing uh, j anything, it is more of j theta 1 because theta 0 is 0 in this case, right? Now further you look at a particular model. If you look at this model, the parameters are w and b. The cost function is like this. The goal is to minimize this cost function, right? So when b is not given, right? So fwx is simply wx. B is 0. So it means that straight line passes through my origin as such 0, 0 part. Because if this is 0, x will become 0. So there is no intercept. So this particular thing will be 0. So now this particular function, when there is no b, this particular function becomes only a function of w, not the function of b. So you simply write xi, apply w on that, minus yi square. That's all, right? Now we want to minimize jw because b is anyway 0, right? Here b is something. The line is not passing through that origin 0, 0. Because b has certain value, even the first one goes 0, the b will give you some value of fwbx, right? But if this goes 0, then it only becomes a function of w. the other parameter. Then we want to minimize this particular thing, right? So you look at this particular aspect. When W is 0 and B is 1.5, of course, you will get a line like this. And you will always find out the prediction to be constant, which is 1.5. May not be a good model, right? Then you have 0.5x. You don't have B there. You don't have B. B is 0. Right? So if one particular weight is 0, the other is 0. So W is 0.5 and B is 0. This is the kind of line that you are going to get. And if W is 0.5, B is 1, then this is the line. This is a combination of these two lines. So from here it is starting and here it is ending. And now you see how the cost gets changed when you are actually varying these aspects, right? Look at this particular portion, how the cost function is changing. When you don't have any intercept, right? The first equation do not have any intercept. It is passing through 0, 0. So B is not there. Theta 0 is not there basically if I talk about, right? So JW is the only function left out, and this is what how it will turn out to be, and this is what exactly you will get. If every point lies on the line, there is no error in that. The prediction, whatever is made, is exactly matching. So your model is excellent, right? Because it is passing through each and every point, model is excellent. That is why this is all 0 square plus 0 square plus 0 square with respect to every point. So J1 is 0. When you look at the second part of the model, right? Second, the cost function, if you look at this, again, it is passing through region, but W is 0.5 in this case. So this is the line. And if this is the line, there are residual errors. 0.5 minus 1 square, 1 minus 2 square, 1.5 minus 3 square. This is what is the residual error. So if you look at this function of W, right? Here it was 0 error, right? Sorry. Yeah. Here it is 0.58, right? Somewhere around this, right? First thing was 0. And if you take the third portion, right? Where this is the line, the error is 1, 2, and 3. 1 square, 2 square, 3 square is 2.3. So basically, given a particular values of theta 0, theta 1, right? What we are trying to do is we are plotting a function. We are plotting a function. And function, this particular cost function is actually has become a bowl shaped function which has got this minima. So the objective is I want to find out those parameters of theta 0, theta 1, theta 2 and all at this point. So the W value, right? Which particular W should I go ahead with, right? That is given by this graph. So one way we said closed form solution. Another we are saying is I am going to put up some values of theta 0, theta 1 and so on, and just checking how the cost function graph is getting plotted. So I got For w is equal to 1, I got this particular value, right? W was 1 here. When w was 0.5, what is the cost function that I got is, that is what we have plotted, right? So when w is 0, what is the cost function that we have got is, that is what we have plotted, 2.3, right here. So if I do with varying this, right, by taking w as 0.50, 1.52, 2.5, this is what I will get. Right? So why this is being shown is, right, because we have, this is a bowl-shaped function. So the goal of this linear regression is I want to minimize this JW portion, right? In general case, if I talk about JWB portion, and with this has a minima at this particular point. So how do we go about it? This is what we have already seen, right? So we want to minimize this. So there is an approach known as gradient descent approach, right? Which is very, very practical and used in machine learning. It's a very generic optimization algorithm capable of finding optimal solutions to a wide range of problems, right? What you typically have is, you say, we have seen there's a bowl-shaped function. The bowl-shaped function has a one global minima actually, right? One global minima. So what you do is you start with some random values of the weights, and random values of weights will give you some value of the cost function, right? Let it like this. What you can do is, you want to achieve this minima, right? You have started here. Slowly and slowly, in iterations and iterations, you are actually stepping towards the minimum point. So you start filling theta with some random values, and then you improve it gradually by taking one baby step at a time, attempting to minimize that particular error or minimizing that cost function. And the moment, okay, you change further theta, here it will be minimum. The further you change the values of theta 0, theta 1, it will go beyond. Again, this will start rising in the other direction, right? But it will go away from the minimum value, right? So at that point, you need to figure it out. Yes, now I'm diverging. So this is the best point and I should retain these values. So this is known as, there's one hyperparameter, right, which is used. Hyperparameter means, because the algorithm will learn the minima, right? How fast it will learn. I'm taking some very small steps, right? And that step size is fixed, I have done, right? If you look at this diagram, very, very small steps I am doing and moving towards this. It means the learning rate is too small. Algorithm will definitely converge because the length is small, and but it will take a lot of computations, right? Too many iterations to converge. If I take very large, I have this value of the cost function, and then I have second as this, third as this, fourth as this. What has happened? My learning rate is very high. I know from here to here it is fine, from here to here it is fine. But from here I am moving there, I am skipping this point because my learning parameter alpha, which is typically we determine, right? It's high. When it is high, so it will keep on oscillating. Now it is gone there, right? From here, it is, if you even look at it, this particular point, not even here, if I say from here, it has gone there, there, and so on, right? So this learning rate is bit high. When the learning rate is high, this is actually oscillating between these two, and it is not going to achieve this. And it failed to find it a good solution because I am taking big jumps. The idea is to start randomly and gradually take appropriate smaller jumps. If it is too small, you will converge, but it will take a long time. If you take it very large, you might miss the global maximum, the global minima, and your function may never converge. Right? We call these as a convex functions. I mean, why we call them? You take any 2 points on this curve, you draw a straight line, it will always lie above the curve, right? So those are convex functions. If you rotate it by 180 degree, this will become a concave function and so on, right? What are the pitfalls of gradient descent? We've just seen the approach, right, as of now. Don't worry. So not all the cost functions look like nice regular balls, right? So this was a bowl-shaped function which we were talking about in this slide, but this is not a bowl-shaped function. If you look at this particular slide, right, the function could also be like this. What it has is one minima here, because the moment you start learning from here to here, it will find out, okay, I'm increasing my cost, so I should come back here, right? But global minima exists here. Global minima exists here. So it will converge to this point. Rather, we want it to be converging to this point, and that is a big drawback of gradient descent. So there may be holes, ridges, plateaus, and all sorts of irregular terrains, making the convergence mm, uh, to the minimum very difficult, right? Minimum is this global minimum, but it ends up in a local minimum. Second is, if the random initialization starts the algorithm on the left, then it will converge to a local minimum. Right? If the random initialization starts on the left, as it mentioned, right, it will go towards the global minimum, local minimum, right, which is not as good as global minimum. If it starts on the right, it will take a very long time to cross the plateau. See, slowly it is learning, slowly, and then it is done. So if you stop too early, you will never reach the global minimum again. So these are some of the challenges with respect to gradient descent, right? Though it's a very practical approach. So if you look at the functions, right, as I mentioned, these are bowl-shaped functions largely, for which we are trying to find out the global minimum. Now this is a 3D plane, right? And plane has a minima somewhere around here, right? So my objective is to find out that minima. So at w is equal to -10 and maybe b is equal to -15, I'm able to find that, right? Because these are bowl-shaped functions. Bowl-shaped, there is one global minima. There is no multiple global minimas as such. Now look at this particular graph. This is a price, this is a size, as I mentioned in my earlier example, right? Now what you've done is you said that, okay, I'll go ahead with this line. And you have chosen these random weights 900 and 0.1, and you said, okay, this is my theta 0 and this is my theta 1, and now how the gradient descent algorithm will work, right? Because this, for this function, we want, this is not the right line, as you can see also, right? This is not the right line, because the convergence is towards this. If you see the cross points, it's more like this, right? What will happen? How the gradient descent will work, right? This is function of parameters theta 0, theta 1, j theta basically, right? So if you look at this 900 and 0.1, this is what theta 1, this is what theta 0, and cost, this is what the well point you are getting, and this is at this particular thing. You want to reach to this particular thing. Now look at this. Then I came up with this line, right? By updating theta 0 and theta 1, this is what gradient descent will do largely. It will update theta 0 and theta 1 in every iteration to a small extent. And this is what you observe, right? That this has become a straight line now. So if you look at this, now my theta 0, theta 1 is almost 0, right? But theta 0 is close to 500. Further, if you look at this, this is the line that I have achieved, right? Again, it is 500, and theta 0 is a bit between minus 0.1 and 0, right? Look at this portion. Now this line is coming toward the most of the points, right, are now aligning with the line. So this is the level, right? I have reached to this particular line now. Further, yeah. So this is the point I wanted to reach, the minimum point, and that is what I have reached over iterations. Now, if you see, this was a bad fit, right? From here to here. But that's a random initialization of weights. It could be a bad fit, as bad as what you can see here, right? But we want a good fit which passes through most of the points as is drawn here. So look at this second iteration. It has come up to a straight line which may be a little better than this, the blue line, right? Then it has come more closer, right? By sort of, there's no significant improvement I can see, but yes, a bit of it you can say, right? Or if the alpha is large, right, probably it might have crossed that. And then finally, it is converging, right? So slowly and slowly, it is actually converging to that particular point. This is what they are trying to say. Point of global minimum. So if you choose any initial value of theta, until we reach a minimum, choose a new value of theta to reduce j theta. That's it, right? You look at it. Slowly, you've started from here. Your global minimum exists here. You see it has traced a path like this in every step and reached a global minimum. Now you see, and there is another path of minimum, right? That is towards this side. Right? So there are minimas. So this region is not that smooth, right? It is up and down, up and down. So this is kind of local minima, you can say, but this is kind of global minima, you can say, right? Choose initial value of theta until we reach a minimum. Choose a new theta and try to retrieve. Since the least square objective function is convex, right, or concave, we need not to worry about the local minima. So whatever the function that we are creating, right, these are either convex or concave. When you have concave or convex functions, we need not to worry about locals minima, right? Because there is no local minima. There's only one global minima there. So this may not be a convex or a concave function, right? Concave will have a maxima, while convex will have a minimum. Look at this, right? I have started with any dates, right? I am subtracting alpha times this particular drift. Small update in every iteration. So you look at this, I've started with these weights. Minima exists here. So I want to reach here. Right? Alpha learning rate is small, 0.5. How much the step size is, that is what is determined by alpha. From here to here, right? This is what will be determined by alpha. Look at this, initialize theta, repeat until convergence, right? So these are the steps that we need to take. Now, what is j theta? We already know that. J theta is h theta xi minus yi, right? Now, when it comes to this theta, when you solve this particular equation, right? Summation I is equal to 1 to n, k is equal to 0 to d, theta k xi k. So basically, your number of you can say the features that we are taking, right? So this is for the ith observation, the k features, right? K is equal to 0 to d. So basically, uh, there are d features within it. So k is another variable that they have taken to represent the variables, number of features, right? Theta k xk minus yi. So first observation, first prediction minus first actual. So you are just taking that particular thing, right? Curly theta by theta j. So you have done basically a derivative of this, right? So because this is a partial derivative, theta term exists here. So this 2 will come in the front, right? And this 2 will cancel out with 2, and then this particular aspect again you will have to do the derivation, right? So this is all partial derivatives. So finally what you're left with is 0 to k theta k xk minus yi, right? Now when you look at this, this is only you're left with xij, xij. Because the other thetas are constant, right? You want to update only one theta. So for a particular feature you want to update a weight, only that particular feature will come into picture here. The others will be obviously they'll not have that particular theta. So those terms will be 0. This is all partial derivatives, right? Y does not have any theta. Theta k xk. So we know theta varies from z to d, 0 to d. So at some point of time there will be a feature which corresponds to whose weight corresponds to this, whose weights you want to update, right? So that is what you are multiplying it with, right? So every time you do it right for any multiple thetas, so the weight of that particular theta will be left, right? So this is what the equation is. Theta j is equal to theta j minus 1 by n h theta xi minus yi xji, right? This is what the simultaneous update will happen for all the thetas. So if you want to put for theta 1, theta 1 minus alpha 1 by n h theta, right? Then you take this as x1, right? The first weight. Then next time theta 2, it will be x2. Then theta 3, it will be x3 and so on. So I am going to update the weight corresponding to a particular feature. Right? At the start, each GD iteration, right? Gradient descent iteration, compute h theta xi. Use the stored value to update the step loop. So when the new thetas and old thetas, you see there's a very small difference coming up, which is epsilon, like you can have this as a threshold value. You say, okay, now it has converged, right? Maybe it is coming as 0.00001, right? So it is very small change, right? So in that case, you say, okay, this is converged. This is a distance formula. We have earlier covered it, L2 norm, Euclidean distance formula, right? Now you look at it, this is what the theta 0, theta 1 are initially, right? 0.01, 0.01. Iteration 2, they are updated. Iteration 3, they are updated. And you see, there is an update going on up to 20 iterations, right? So you'll have to see how my thetas are getting updated. That is the gradient descent approach, right? Any questions so far? People who've joined? No questions? Okay, I'll continue then. I'll just wait for 2 minutes because I've spoken enough today. Okay, let us do one example here, right? Though this is one example, we are starting with theta 0, theta 1 and then gradually updating it, right? Let us take a simple example. X as 1, 2, Y as 2, 4, right? I am taking theta 0 and theta 1 initially as 0. I can take anything, right? Both I am taking 0. Alpha as 0.1. That is my learning rate, right? Now, at x is equal to 1, right? What my prediction is theta 0, 0 plus 0 into 1, that will be 0 because theta 0 plus theta 1 x. X is equal to 2, 0 plus 0 into 2, again 0, right? But what is the error? You look at this 0 minus 2, 0 minus 4. So if I see this, right, minus 2 and minus 4, right? What is the average error? If I say 3. Average error is 3. So theta 0, how I will update is 0 minus 0.1 into minus 3. This will be 0 minus kind of a 0.3. So theta 0. So this is minus 3. This is minus again. Sorry, this will become plus. So theta 0 is 0.3. If I have to update theta 1, I have to see the error of theta 1, right? Minus 2 into 1, right? Plus minus 4 into 2. Because the output for the second is, if you look at minus 2 minus 4, right? So now this is theta 1 x1, all right, theta 2 x2. So theta 1 x1 is minus 2 into 1 minus 2, minus 4 into 2 minus 8, so minus 10 by 2 minus 5. So theta 1 is 0 minus 0.1 into minus 5, that is 0.5. The next equation becomes is 0.3 plus 0.5x. This is after first iteration. After second iteration, right? If you look at this particular thing, right? How to update? So we are applying this, right, as theta xi minus yi multiplied with that particular xj. So theta 0, theta 1 has come, right? And in the iteration 2, you can continue doing this and update those parameters. So this is how the gradient descent actually works, right? But in Python, you just have to give it a method call. This will be done, right? So look at this. Now we will understand the intuition behind this gradient descent, right? When you look at f of x as minus 0.15x in 500, right? This is the line that we are fitting, right? But this is not a good line. We all know, right? This is not a good line. So you are somewhere here, the minima exists somewhere here, you want to go, right? So overall, now what will you do? You will update the weights. You see, from this line, you have come to this line. From this line, you will gradually have come to a straight line, right? Right now, straight line is a bit better. And now you see you are started gradually moving towards the point. You see slowly and slowly you are moving, right? Finally, you got this bit, which is the minima value that you have got. So f of x is 0.13x plus 71 there, right? So you look at this. Slowly and slowly you are moving towards this. This is close to 71 and 0.3. So this is how the gradient descent looks like, right? 900 minus 0.1x, these are the parameters, and then you see gradually how this is improving. You are somewhere here, then second time you have come about this line, you have moved a bit, right? Third time you have come across this line, you have moved a bit, third point. Fourth time you have come across this, you have moved. I mean, this is not the fourth, maybe slowly and slowly you are gradually moving towards the center, but this is how, and some iterations are being skipped right here. But you can always plot this and see. At least this gradient descent function you can try within Python and see how the things are updating. Now you look at this again, minus 0.1 plus 900, right? So we started with something different here. Point of minima somewhere here. Now let us see how the things will move, right? So you see the second line comes in, third line the green one, fourth one the red one. And then you see slowly and slowly, gradually and gradually, the weight updates is happening and the cost is decreasing. The moment you update the weight, the cost should decrease, right? So you see, iteration by iteration, it is coming. This particular thing, like choosing alpha is very, very important. If alpha is too small, you may end up in a very slow convergence, but alpha is very large, then you might oscillate between these two, right? So from here you have moved here, and from here maybe you're moving here, there, and so on. So may overshoot the minimum, may fail to converge, may even diverge also, right? To see if the gradient descent is working, print out j theta after every iteration, the value should decrease. If it does not, adjust alpha. So with respect to the iterations as are growing, you can reduce the value of alpha. Initially, it may be high because you are very far from the minima. The moment you come closer to the minima, you want to reduce this alpha, right? So you see alpha 0.02, how the learning is happening slowly, right? After some iterations. You see alpha 0.1, learning is bit fast, right? You see alpha 0.5, this is too high. So from here, the line has moved towards that side. So these lines, the actual line has been skipped, right? This is what they are trying to showcase. So you have to choose an alpha, appropriate alpha, right? That's the learning rate basically. Gradient descent can be slow when the feature scales are widely different, right? So when we say feature scale, so maybe one feature has value 1, 2, 3 up to 10, right? Another feature, the value is starting from 1 lakh and ending up to 10 lakh, right? So the scale is quite different. When the scale is quite different, obviously when you will see the difference between these two, right, it will be large, and of course then the convergence will be slow. So it's better to normalize the features, which we have seen earlier also, that you normalize them, right? Then the algorithm will converge faster. Now, next come is the batch size, right? How much batch of data that we are taking, right? This also impacts the rate of convergence. So there are three variations of gradient descent that we see. One is batch, another is mini batch, third one is stochastic gradient descent. So what is the difference in C? Let us see that. In a batch gradient descent, entire training set is used to calculate the training error, and that too in each iteration, right? So gradient is calculated and used for weight updates. Convergences in the least number of iterations, convergence, right? And the rate of convergence is the highest. Computation requirement is also high because you are using the complete training data. Memory requirement is also high. Stochastic gradient descent, random selected training instance is used. You are not using complete, but random selected. But this will take most number of iterations to converge. Rate of convergence is lowest. Computation requirement is lowest because you are going to choose some random sample. Memory requirement is also lowest. Okay. Third is mini batch. You actually pick up a subset of training data of size, say 64, 128, 256 is used in very efficient implementation, possible leveraging vector processing using GPUs also, right? So stochastic, you are, it's a kind of mini batch, sorry, not stochastic, mini batch, right? You are picking up a subset of training data, right? And this is an efficient implementation than the others. If you look at the stochastic ones, you see how many iterations the red ones is taking, right, to converge. But when you look at the green one, mini batch, right, still these iterations are more than the blue ones, but the computation per iteration is less, right? And the blue ones, though it is taking the least number of iterations, but computation per iteration is very, very high, right? So mini batch gradient descent is preferred. Next is polynomial ones, right? Extending to a more complex model. We have seen linear models, right? Where I was saying the equations are of theta 0 plus theta 1 x1 plus theta 2 x2 and so on. But there could be a possibility of a polynomial transformation, right? You might have an equation like this, x square plus x cube and so, right? Now, what should we do in such cases? That's very, very important to understand how to move to a polynomial regression. So in linear regression, the relationship that we assumed was linear. House prices increases linearly, right, with the area. But it may be possible that you may have a quadratic relationship, higher order models, right, as you are seeing. So in such cases, you might need to fit a polynomial curve rather than a simple linear regression, a straight line, right? So what do you need typically is you need to expand the model, right? Look at this. Instead of fitting a straight line to these set of points, we are trying to fit a curve, more like a sine wave curve, right? Quadratic would be theta 0 plus theta 1x plus theta 1x square. Cubic will be around theta 0 plus theta 1x plus theta 2x square plus theta 3x cube. In general, it is mentioned here, right? The quadratic, the polynomial ones, right? So example could be, let's say you want to predict salary based on the experience. The reality is initially in the initial state, when you join as a fresher in the organization, the salary rises are very quick, right? but at a mid-age career, the growth actually slows down. So in such a case, it's not a linear relationship between experience and the salary increase so that you can easily fit a straight line. Rather, it's a little more complex relationship. So straight line may not fit in such a case. So you will have to come up with a polynomial curve. Right. So if you look at this particular thing, right, which is showing the quality of fit and all, why we are moving to basically these higher order or the polynomial curve fitting is you have a straight line in adjusting these points. So there are some points which there's none of the points which lie exactly on the line, right? So if you look at this curve, there's some points very close to the line. If you do this one, right, this is passing through exactly each and every point. Now there are concepts used which is known as underfitting, right, and overfitting. When you go with the underfitting, right, it means the model has not learned your training data, right? There's a higher training error. That's an underfit. Then there's an overfitting that there is no, I mean, very less training error. You see the curve is, but the curve is very, very complex, right? And when you have an underfitting, right, it is more of a high bias issue. When you have an overfitting, it's a more of a high variance issue. So overfitting is the learned hypothesis may very well fit the training data, but fails to generalize the new examples. That's what an overfitting is, right? So how do you address the overfitting? So far what we've covered is we have come across two techniques to solve linear regression problems. One is closed form solution, right? Using matrix equations and all that we see. There are no iterations, we directly get the best parameters, but for smaller data sets, it's good. For larger data sets, computing inverse of a matrix, transposes and all, it's quite computation heavy. So another method, gradient descent, was proposed. When you choose different thetas, right, you plot a cost function graph. It is largely a bowl-shaped graph. So for a bowl-shaped function, the problem actually can be converted to finding out a minimization in a bowl-shaped function, right? And then gradually update the weights, right? You can start with any initial theta parameters and gradually you are moving towards uh, the minimization, right? And for that you have to choose the learning parameter alpha. Alpha has to be chosen as very appropriate. If it is too large, it may oscillate and may never converge. If it is too small, it may be very slow convergence. So it has to be appropriate. The best thing is you can have initially alpha value and decrease it over iterations because we are moving towards global minima. When certain number of iterations are passed, I am more close to my target or the global minima. I should not have a very large value of alpha at that time, so I can decrease when the number of iterations are uh, when I have certain number of iterations are completed, right? Then we came up with it's a linear regression. It may not be linear regression always because we may come across an input data set where the linear simple straight lines do not fit. We may have to fit a higher degree polynomial curve. It could be quadratic, cubic, right, and so on. So, but if we try to fit a polynomial curve, sometimes what happens is we may end up in an issue known as overfitting, where the curve tries to pass through each and every training sample. If it happens right, the curve or the model fits very well to the training data, but fails to do generalization when the test data is given. It fails miserably. So this problem is called overfitting. Now, in order to address overfitting, we are going to cover two more types of regressions, that is lasso and ridge regressions. Instead of minimizing the cost function, we'll add something so that the weights which the model is going to learn, they remain within certain bounds and we don't end up in overfitting. So these are the number of input features basis which I'm going to determine the price of house. And now you see there are 100 features. And this is the price in house, right? This is a two-dimensional plot, size in square feet and price in thousands, right? So how to address overfitting? When I have so many features, right? So it might be possible that uh, it is memorizing each and every feature in the training data, right? But there are certain irrelevant features. Maybe that could be there. Average income in the neighborhood, such as, right? This is may not be very relevant, right? As such, or if I'm, let's say, predicting student marks main basis study hours and attendance, right? And then there is a name of student. Name of student cannot predict, I mean, cannot contribute towards increase or decrease in the marks as such, right? So if there are some irrelevant features, right, this can lead to kind of an overfitting thing. Can we reduce the number of features in some way? Manually select the features which one to keep, or let the model select, right? There are certain algorithms which will select certain features, right? And then they build the model. Other option is regularization. Keep all the features, but reduce the magnitude and the values of parameters theta j. This works well when we have a lot of features and many of which contributes to better predicting y. Now, see it carefully what we mean by lower order model and high order model as such, right? So what do you see here? There is a training set, there is a validation set, right? So what is happening is you are increasing the training set size on this side, and this is RMSE. Root means square error. So when the training examples are small, you see the root mean square error is high, right? Then the moment it has come to 10, you see kind of decreasing and then increasing and decreasing and so on. This is a validation set. So you see the RMSE value for the validation set, right? When uh, there's a very small training examples you use, the validation set has very high error. The moment you increase it, right, to a certain extent, this is sort of decreasing, and then it becomes stagnant, right? Then it becomes stagnant. Okay, now let's look at this particular model. When higher size of training data set needs to be large to prevent the overfitting. So when you have this large data set, right? So what you are seeing is when you are putting this larger data set, right? The issue of overfitting is getting reduced because with respect to the training and test data validation set, the error has come almost similar, right? I mean, with respect to training, this is the error. With respect to test, this is the error. If you look at a higher order model, this is a lower order straight line model, probably, right? A simple model. This is a higher order polynomial model. If you look at this, the error is with respect to training is 0, right? The moment you have this many training examples, right? bit it increasing a bit, right? And then gradually when it has this much samples, training samples, it is stagnant. Same thing if you look at with respect to this particular what I can say test data, right? Initially the error is high because the training examples that you have used are very less. Even it is further exaggerating because the model is complex, right? So it is failing to generalize. The moment you are increasing the data set, right, the test error you see is drastically increasing because you have increasing the training examples, test error is decreasing. When you see the model parameters learned with this much training and it's this much is the error that we are getting. So basically what this chart is indicating is the more you add the data, the training and test error, they converge, or the validation error, they converge basically, right? Whether it's a lower order model or a higher order model. So if you increase the training data, it kind of prevents the overfitting. Here we will say the smaller data, right? If you see with respect to, if I talk about till this point, right? Let me take this one. Training error, sorry, test error is very, very high. Training error is very, very low. Less than 0.5. This is more than 3, right? So huge difference, kind of overfitting. The moment you increase the data, you see that this error is increasing while this error is decreasing. So basically they're converging. So adding more data helps to prevent overfitting. Polynomial fits can lead to overfitting. This is what this particular diagram shows. Polynomial order of 300, right? This is the dotted ones. Sorry, the green ones, right? So you have a straight line with the red and the curved line, the dotted ones, right? So what typically the straight line does is it is showing underfitting. The curve, the blue dotted lines, it is more generalized model, I would say. And when you do this one, polynomial of degree 100, it is trying to pass through each and every point smaller, the green one. You see how complex the function it has become, right? This is known as overfitting. So my model should be neither too simple nor too complex. Very simple model may result in underfitting. Very complex model, of course, it will result in overfitting. So what we can do is we can use some regularization, a method for automatically controlling the complexity of learned hypothesis. So what we want is penalized for large values of theta j. We can incorporate it into a cost function, works well when we have a lot of features and each that contributes to bit predicting the label. Can also address overfitting by eliminating the features, right? You look at it, my cost function will not remain this now. I am also adding this lambda by 2 theta j square. Now I want to minimize this. What is lambda now, right? Now this is an equation of basically a ridge regression, right? This is regularization strength, the lambda or the parameter, right? No regularization we are putting on theta 0, right? So we are trying to punish the large weights. Whatever the weights will come here from this particular equation, right? Some weights will come. And I am going to put lambda by 2 plus theta j square for that scared weights. So if there are very large weights, basically I want to punish them. Punish them means I want to keep them into within a certain bounds. Look at this. This is the equation. This equation, now, why, with the addition of this, how the weights can be reduced, right? That could be one question that you may have. I am going to minimize this. When I am going to minimize this, I'll have some theta, right? When I am adding this particular thing, now with this theta, right, I'm going to have some theta and the theta values can be high. I want those theta values to be in a certain range, right? So then I have to use this. What happens if we set lambda to be huge? Example 10 raised to power 10. Again, the content is being taken from a very popular course, right? So look at this. This particular diagram, what it says is an overfitting curve, right? This is an overfitting curve because my lambda value is too high. Lambda value is too high. So you have some error function plus the penalty that you are adding yourself, right? Look at this particular thing. Now, before I even do this, right, let me solve a numerical bit so that I am able to explain it in a proper way. There's 6 people who've joined. Not sure if they are Vasu has joined. Vasu, you've joined so late, may I know the reason? I told you this is going to be completely mathematical. Join on time, have pen and paper handy with you. Otherwise, how you will now learn this? This is extremely important and the core of this regression, what I have covered today. Okay, it's up to you, right? I'll see if any questions are coming and anything is coming, right? Then I'll come to know about it. Okay. Now, instead of the cost function, which I was saying, right? I'm adding this lambda plus theta j square, right? Lambda is my regularization strength. Theta square is the scared weights. So large weights get punished. Punished means we want to bring them down. But the important is thing is that we don't want the weights to become exactly zero. Weights rarely become exactly zero, right? That's another thing. Now, let me take an example. Y is equal to theta 0. I'll take a simple example. Theta 1x, right? Now, without regularization, right? Let's say theta 1 is 10. And let's assume this could be a large weight which can overfit. Now, lambda value is 1, let's say. Right? Lambda value is 1. So, if theta 1 is 10, 10 square, theta j square is 100. Right? Theta j square is 100. So now j theta will become sort of, if the mean square error was 20, the first term, right? Second term will become plus 1 into sort of 100. Let me take if lambda is 2, right? Or let's say 1, right? 20 plus, let's say 50, it will become 70. So what is it? The cost is still high. So what model will realize this is a large weight, right? Costly. So the optimization will reduce the weight further. Optimization. So this is something extra I am adding so that weights get reduced. Right? Cost function, no doubt it was a bit low, right? It was okay. But since this I added this, right? I want those parameters to remain in a certain bound. So that has been added. So if I put theta 1 as 4, 4 will, the square will be 16. 16 by 2 will be 8. 8 plus 20 will be 28. And then cost has reduced, right? So ridge, what it is doing? Further reducing the cost, right? And further reducing the weights. So if I put theta is 4, 4 square 16, 16 by 2 is 8. So it is reducing the weights actually. That's I wanted to show you that it is reducing the weights. Now, if I put this lambda value very, very high, so this term will become very, very high, right? And eventually what will happen is we will say, okay, we'll have to put theta close to 0, right? Because this term is very, very high. So the cost is very, very high. So if this becomes too huge, right, lambda, then I'll have to set the weights to be 0. I mean, the weights will start approaching 0. Right? So what this particular diagram is showing is these are the points. The curve one is an overfit model. The straight line is an underfit model, right? So if you set this lambda to be very, very high, you sort of end up in an underfit model, which will sort of have this kind of line, right? Because everything is 0, so only theta 0 will remain, right? Because theta 0 we are not disturbing here. So it will become a kind of a straight line if all my parameters become 0 and theta 0 is the only one left. So you look at this, right? The same thing is being explained in a more intuitive way. So this will become 0, this will become 0, this will become 0, this will become 0. Ultimately, you get this straight line, right? Because only theta 0 is the one which will remain. That is why we are not adding theta 0 here, right? The intercept thing we are not adding. So this is with respect to ridge regression, which scares them particular weights, right? And if you want to update the weights, right, with ridge regression, you will update it like this. So this is one more parameter added, right? You want to solve this, you can step by step solve it using it's just a simple mathematics things, right? These terms we have already covered, right? So we're just reducing this right now. So lambda by 2 is 1 by 2 and all those things, right? So you can take that as such out, right? And then you see this is what you are left with, gradient update. Initially gradient update was this only, but with addition of this, gradient update becomes this. So this is your regularization parameter that you have added. Lasso regression, right? This phenomena is simple here. When you come to lasso, right? Another part is when the lambda becomes 0, then there is no regularization, right? Then it's whatever is there will remain as such, right? So when it comes to lasso regression has again that regularization parameter, but this has a weight theta, and this is not a scale. Same thing we are having here, but the weight is not getting scared. So rather than scaring it, if you have something, right, you simply have the sum of those weights added to it. That's all. Plus this lambda as some parameter. So if you see this lambda is equal to 0, right? Means there is no regularization. So this is a blue kind of a model that you are getting with some lambda 10, right? So this is the model that you are getting, the green one, lambda 100. So you see it's a high regularization parameter that you are adding. So it is getting flat. So weights are approaching zero now, right? So if you look at this lambda value right here, so you see lambda is zero, no control, so overfitting, right? When you put lambda as smaller one, still there is an overfitting. Then lambda is 1, then you are able to control it a bit, right? When you look at ridge, right? When you look at ridge regression, lambda is equal to 0. No regularization, the normal thing that comes in. Lambda 0.1, small change, right? But when you put lambda as 1, see, this is exactly that where it has come in, right? Weights are not appropriate, right? When you put lambda is equal to 1. So this is where you are highly doing that part, what I can say, the weights are shrinking basically, right? So what they're saying basically is model is shrinking the weights. If the lambda is 0, there is no regularization. Lambda is small, right? You see that there is a small weight shrinks in a very small proportion, but the moment you increase it, the weights start approaching 0, kind of a thing. Same thing goes here with this, right? So this is ridge, this is lasso. So this is the exact model. So when you have put this, right, you see with the lasso, still there's a curve, right, going on. It was a this much curve, but now you see this is a curve going on. And with ridge, you see this is the line coming in, right, when lambda is 1. So lambda 1 will remain same because lambda square is also that. Right. So when you increase lambda, some weights will definitely approach 0. Right? Don't overtrain to prevent overfitting. That's another way to early stop. Stop training once the error on the validation set starts showing an upward trend, right? Even if the error on the training set keeps decreasing, but on the validation set, if it start increasing, you see here, training error is getting decreased with the number of iterations, while the test error is also decreased to a certain point, and then after that it start increasing. So we can stop here. This is what they're trying to say: early stop, better convergence. That's all. Then comes this bias variance trade-off. It's a way to understand overfitting and underfitting. So if it is too simple, right, the model will have an underfitting and it will not be able to predict on the test data, right? Too simple. It is too complex, right? In such a case, uh, it will very well learn the training data, but not be able to fit your, what I can say, it will not be a generalized model. It will not perform very well on uh, the testing data, right? So the term bias, right, what it means is this is an error because the model is too simple. That is what bias is. So when you have a high bias in a model, there are strong assumptions and it misses out important patterns, right? So you have a simple classifier, right? It has a high bias. If you see here, simple classifier, this is a complex classifier, right? So you are kind of reducing it when you are moving towards a complexity, right? This is the point where you see that, okay, this is further start increasing. Now, second thing, I'm using the term variance, which means model changes too much with the training data. So high variance model will become too complex and it actually memorizes the training examples and it will fail on unseen data. Error or loss on the training data set, right? Detrain. Error or loss on the unseen data set, that is t-test. So the first is overfitting, second is underfitting. So when you have a test data, which, I mean, there's a loss on the test data is high, it means it's overfitting. Loss on the training itself is high, it means it is underfitting. So what we want is, we want low bias, means we don't want underfitting models. We want low variance, means we don't want overfit models. We want to use a better, balanced approach, neither too simple nor too complex. You look at this particular model. This is high bias. See, you see, it's a straight line, right, with a high bias. That's an underfit because the training error is high, right? When you go with this has a low bias. And not exactly low, this is the right fit model. And when you do this has high variance and low bias, right? So training error is low, but testing error will be high. Here training is low, right? Testing is also low. So this is a balanced approach. While these two are, this is underfitting with high bias, right? This is overfitting with high variance. Means you change the data, model changes, right? That's what it means. So when you have a high bias, right, then of course you consistently miss the target. Same mistake you will repeat, and model will be consistently wrong. And when you have high variance, right? Look at this underfit low variance model, right? Like this. High bias, underfit. J train will be high. J train high variance overfit. So test error will be high, right? While the J train may be low, training error may be low. High bias, high variance. J train will be high. This will also be high. So what they're trying to showcase is we have their low bias, kind of low variance kind of a thing, right? But here what we have got is high bias and high variance, right? So training error is also high, and even after that, JCV, right? Test errors has also become high. So if you look at this curve, this is a the dark blue one, right? Passing through each and every point. Overfit. This is not passing through each and every point. Underfit, right? So overfit has a high variance, underfit has a low variance. So if you look at this part, right, degree of polynomial. So as you will increase the degree of polynomial, model will kind of learn the overfitting part, right? So if it is high variance, JCV may be greater than JTrain. So if you look at this particular model, right, JCV, it's greater than JTrain. It's kind of overfit model, right? High bias, meaning that more underfittings. High variance, so JTrain will be high, JCV will also be high, right? So this is little more about bias and variance, right? So CV is about testing, right? Validation part. When you do linear regression with regularization now, I think I'm just, let me see how many, 3-4 slides and then we are winding up. Not sure if you are there, but let me check. The moment you miss out a session here, right, and if you don't do self-study, it will be hard for you to catch, because highly conceptual thing, mathematical, right? And then on top of that, programming, it's an intersection of multiple disciplines, right? So you have to be on your toes always with this course. Okay, let me again a little more dig down into bias and variance part, right? So if you look at this, this is underfitting model. JTrain is large. So larger lambda, if you put high bias underfit, right? So if you do regularization, a high value of lambda causes the weights to approach zero. This will result in underfitting. Intermediate lambda will result in this, right? So this is the kind of model that we are expecting, where JTrain is also small, this is also small. If lambda is very, very small, JTrain will be small, but state test will become very large, and this is what we do not want. So same thing being told in different ways. Now this is with respect to regularization, right? Choosing the regularization parameters. You see, try lambda 0. Lambda 0 is no regularization basically, right? Then with lambda 1, you try the test error and see if it is increasing or not, test error is decreasing or not. Then with lambda this, you can try, lambda this, you can try, right? At this particular lambda is equal to 0.008, right? And then try lambda 10, 12, and so on. So these weights are getting updated. So the moment you see, okay, at certain lambda, now the question is how I decide, okay, this much lambda is good. Lambda, what it controls is the regularization parameter. What do you mean by regularization parameter? There are two regression methods we have covered, lasso and ridge. Ridge, right? They both do not allow the model to go with underfitting and overfitting, but there are parameters within that. If I don't control their weights and all, I mean the values, then again the overfitting, underfitting can happen, right? So we have to look at from those perspectives also, right? So you look at this, try lambda is equal to 0. What is the cost, right? Try lambda is equal to 0.01. Am I reducing the cost further, right? And then what are the weights learned? And the moment you see, okay, at this lambda after this, right? Uh, probably the test error is getting changed, right? Test error is getting increased. Then you say, okay, I'll stop at that particular lambda, right? So then if you, that will be kind of a good fit model, right? For that particular lambda, right? So you are trying to put some values of lambda, increasing lambda. The moment you increase lambda, weights will go down. Weights will go down, mean that overfitting we are trying to reduce. And the moment the weights we are reducing, with reduction of weights, if the test error increases, it means I'm started losing my generalization. I should not further reduce it. That's what it is. Right? So what is the error? Is that error fine or not? That is what we need to check, right? Bias and variance is the function of regularization parameter. So now they are representing bias and variance with respect to that, right? So you look at it, this is one function, right? Cost function that they have written. This is what the J-train means the training error. The training error, right? When you have a variance, right, within that, you see, I'm coming here. This is the optimized lambda that I'm getting. The moment it becomes going in the other direction, right? And then I am reducing my weights, right? With increasing lambda, I'm increasing the bias there. From here, I'm reducing the variance because variance leads to overfitting. So I'm reducing that. I've reached the minimum point. After that, I've started in the other direction, right? Maybe I'm reducing the variance, but I'm increasing the bias there, and that is not my objective. So this is what is in terms of variance on one side, bias on the other side. I have to go with minimum variance and minimum bias there, and that value of lambda that I have to choose. So if I choose very large lambda, this is what is likely to happen. Weights will go zero, only that particular theta zero will have its impact. If I go with very small lambda, then overfitting is likely to occur. It is passing through each and every point. So now debugging a learning algorithm. You have implemented a regularized linear regression on housing prices like this, but it makes unacceptably large errors in predictions. What do you try next? Right? What do you try next? Large errors in predictions. Predictions means on the test data. So what you can try is you can get more training examples. It will reduce the variance. Try more sets of features, right? It will fix high variance as such, right? Try getting additional features. It will fix high bias. Try getting polynomial features, right? It will fix high bias. High bias means underfitting, right? So if I have polynomial features, of course, it will result in a bit of a curve, but yes, try decreasing lambda and try increasing lambda. If you try decreasing lambda, it will fix the high bias. Bias means underfitting, right? So lambda decrease. Increase lambda will fix the high variance. These are all the things that we can try when my learning model is not acceptable. Unacceptably large errors in predictions. Basically, my test error is high. So if my test error is high, I can reduce the variance part, right? That's more important if my test error is high. Maybe if you have joined late, you're not able to follow, you are finding it too complex because these are scary equations and all. Try listening to the recording, right? Keep pen and paper handy with you. Revise your matrix multiplication concepts, matrix inverse concepts, everything of that sort you need to revise. try some problems, right? Maybe I'll see if something can be created, right? Try some problems, and then you will be able to understand it. Try implementing it also on Python. This will help you to gain a better vouch of what I have shown, right? All these curves and all, high variance, high bias, and so on. This you will get because you can plot a cost function, right? Where it is going. All these things are related. So that ends the regression module, right? I will make these PPTs available to you for your reference. This is highly mathematical, right? But not very tough. Only thing is you need to be away from everything and be focused here. Initially, it will be tough. While you give 3-4 readings to it, this will sit in your mind. And then you will be able to solve it. I think you have your assignment also completely on this, and you have listened lasso and ridge regression also included into that, right? So that practically it has been already covered how to do that, but conceptually, mathematically, what these things actually, I mean, these regression, how they solve it, that is now being covered in detail, right? That's all for today's session. We'll meet next week with the next session, right? So be ready. And if you come like this without some self motivation and all, okay, now it is 11:30, I will join by 11:45 and all, then it will not work. Let me tell you very frankly, it will not work. And later on, you say, okay, uh, you say, okay, no, we were not able to follow. There is some level of motivation student also need to put it, right? Because this is a huge thing. And if I get some questions, I can clarify that, right? Not an issue. But if I don't get anything from your end, then I cannot do much. It's up to you now. Then this batch is like I have already taught you multiple times, right? So